Definition of finite sets. So let's begin our discussion on sets. In mathematics, a set is simply a collection of distinct objects, considered as an object in its own right. What this means is, imagine you have a bunch of things, it could be anything, numbers, letters, even other sets, and you group them together. We treat this group as a single thing itself. It's like taking a bunch of individual Lego bricks and building a castle. The castle is now a single entity. These objects are called elements or members of the set. So, those individual things we group together, we call them the elements or members of the set. Going back to our Lego example, each individual brick would be an element of the castle set. Now, sets can be of different sizes. Obviously, some sets will have more elements than others. A set with just a few elements is smaller than a set with many elements. This idea of how many leads us to. This brings us to the concept of finite and infinite sets. Sets can either have a limited number of elements, we call those finite sets, or an unlimited number of elements, those are infinite sets. Think about it like this. A small bag of marbles is a finite set, while all the grains of sand on a beach, well, that's getting close to an infinite set. This tutorial will focus on finite sets. For now, we're going to concentrate specifically on sets where we can count all the elements and arrive at a final number. We'll explore exactly what that means and how to identify them in the following slides. So, let's move on and define what a finite set actually is. What is a finite set? So we've talked about what sets are, just collections of things, and that sets can have different sizes. Now we're going to zoom in on a specific type of set called a finite set. This slide defines what a finite set is. It states that a finite set is a set that contains a countable number of elements. Now, the key word here is countable. What does countable actually mean? Well, it means that you should theoretically be able to list out all the items in the set, one by one, and eventually stop, reach the end of the list. Think of it like counting apples in a basket. You start at 1, and you keep going until you've counted every single apple. In other words, when you finish counting all the elements in a finite set, you'll end up with a whole number. You won't get a fraction, a decimal, or anything else. It will be a number like 0, 1, 2, 3, and so on. Now, let's get a little more formal. Mathematicians like to use notation to express ideas concisely. So, if we have a set, let's call it S. We say that the set S is finite if the number of elements in that set is a non-negative integer. What does that mean? Well, the number of elements in set S is represented by this symbol, vertical bars around the S, which we read as the cardinality of S, or the number of elements in S. So, S simply tells us how many things are in the set. And for a set to be finite, that number, the cardinality, has to be a whole number that is 0 or positive. We'll see this in action with some examples on the next few slides, but it's important to understand this definition first. Remember, countable is the key. If you can list and count the elements and get a whole number, you're dealing with a finite set. Examples of finite sets. Let's move on to looking at some examples to solidify our understanding of finite sets. This slide presents our first example, fingers on one hand. We're going to consider the set of fingers you have on just one of your hands. It's a very relatable example, right? Now, to define this set mathematically, we can list out all the fingers. We represent a set using curly braces. So, we have S equals an opening curly brace, then we list the elements separated by commas. Thumb, index finger, middle finger, ring finger, pinky, and then a closing curly brace. So, the set S contains those 5 fingers. Next, we count the elements within this set. If you carefully count the fingers listed, thumb, index, middle, ring, and pinky, you'll find there are 5. Because we were able to list all the elements and arrive at a whole number, in this case, 5, this confirms that the set of fingers on one hand is indeed a finite set. Finally, we use a notation to represent the number of elements in a set. The vertical bar symbol, which is read as the cardinality of, followed by the set name in brackets. So, we write it as the cardinality of S equals 5. This simply means the number of elements in set S is 5. Remember this example, as we'll be applying the same logic to the examples that follow. We're establishing that if you can count the elements and get a whole number, you're dealing with a finite set. Examples of finite sets continued. Let's move on to another example to solidify our understanding of finite sets. This slide presents example 2, months in a year. We're going to consider the set of all the months in a year. We represent this set using a capital letter, in this case, M, and we list all the months within curly braces. So, the set M contains January, February, March, April, May, June, July, August, September, October, November, and December. Now let's check if this is a finite set. Remember, a finite set needs to have a countable number of elements. Can we list all the months and eventually reach the end of the list? Absolutely. If we count them carefully, we find there are 12 months. 12 is a whole number, a non-negative integer, which satisfies the condition for a finite set. Therefore, the set of months in a year is a finite set. We use the notation, the number of elements in M, which is written as absolute value of M, and we say that it equals 12. So, the cardinality, that's the mathematical term for the number of elements, of set M is 12. This example, like the one with our fingers, demonstrates that if you can count the elements and arrive at a whole number, you're dealing with a finite set. We'll continue looking at more examples, and then we'll recap the key takeaways to make sure you've got a firm grasp of this concept. Examples of finite sets continued. Let's move on to another example to solidify our understanding of finite sets. This is example 3, and we're going to look at the letters in the word math. So consider the set of letters in the word math. We're going to represent this set using a capital L, and within curly braces, we list each of the distinct letters, M, A, T, and H. So, the set L is equal to the collection containing M, A, T, and H. Now let's count the letters. If we do, we find there are 4 letters in the set. Because we were able to count the elements and arrive at a whole number, in this case, 4, this confirms that this is indeed a finite set. Remember, a finite set must have a countable number of elements. We use a notation to represent the number of elements in a set. The vertical bar symbols, which a mathematician would read as the cardinality of, enclose the set name. So, we write the cardinality of L is equal to 4. This simply means the number of elements in set L is 4. This example, like the previous ones with fingers and months, demonstrates the core idea. If you can count the elements and get a whole number, you're dealing with a finite set. We'll continue with more examples, and then we'll recap the key takeaways and address some common mistakes, so you have a really solid grasp of this concept. Examples of finite sets continued. Let's look at another example to solidify our understanding of finite sets. This is example 4, and it deals with even numbers. We're considering the set of even numbers less than 10. We represent this set using the capital letter E, and its elements are listed within curly braces. So, E is equal to the set containing 2, 4, 6, and 8. Now let's count the elements within this set. We have 2, 4, 6, and 8. That's 1, 2, 3, 4 elements. As we've established in the previous slides, if we can count the elements and arrive at a whole number, the set is finite. And we did arrive at a whole number, 4. Therefore, this is indeed a finite set. Finally, we use the notation, the number of elements in E, which is written as absolute value of E and is equal to 4. This simply means the set E contains 4 elements. Remember this notation, as it's a concise way to express the size of a set. This example, like the others we've seen, demonstrates the core principle. If you can list all the elements and get to a definite, whole number count, you're dealing with a finite set. We'll be building on this understanding as we move forward, so make sure you're comfortable with these examples before we tackle more complex concepts, which we'll cover in the next slides. Key takeaways. Let's recap what we've learned about finite sets with these key takeaways. Remember from our earlier discussion, countable means you can, at least in theory, list out all the items in the set and eventually stop. It's not about whether it takes a long time to count, but whether it's possible to finish. Next, this directly follows from the first point. You can list all the elements of a finite set and eventually finish counting. We saw this in our examples: the fingers on a hand, the months of the year, the letters in math, and the even numbers less than 10. In each case, we were able to create a complete list. Finally, and this is a bit more formal, the number of elements in a finite set is a non-negative integer. Now, what does that mean? Well, when you finish counting, you'll get a whole number: 0, 1, 2, 3, and so on. These are integers, and non-negative simply means the number can't be negative. You can't have -5 fingers. So, the size of a finite set, which we denote as the number of elements in the set, is always a whole number starting from 0. Keep these 3 points in mind, as they are the core definition of a finite set. In the next slide, we'll look at some common mistakes students make when dealing with this concept, so you can avoid them. Common mistakes. Let's move on to this final slide, which highlights some common pitfalls when working with finite sets. A common mistake is to assume that any set with a limited number of elements is finite. Now, after going through examples like the fingers on one hand, months of the year, and letters in a word, it's easy to fall into the trap of thinking that just because a set doesn't seem endlessly large, it must be finite. But remember, it's not about seeming limited, it's about being able to actually count the elements. While this is often true, it's important to remember that the defining characteristic is countability. This is the key takeaway. We've been emphasizing that a finite set needs to have a countable number of elements. Countability isn't just about the set appearing small, it's about the possibility of listing all the elements and stopping at a definite number. If you can't, even in principle, list all the elements and arrive at a final count, the set is not finite. This is a crucial point. In principle means even if it's incredibly difficult or time-consuming, if there's no way to create a complete list, it's not finite. For example, a set containing all the students who have ever lived is technically finite. This might seem surprising. There is a finite number of people who have ever lived, even though it's a huge number, but practically impossible to count. Exactly. While theoretically finite, the sheer scale makes it impossible for us to actually determine the number of elements. This is a good example to show you the difference between theoretical finiteness and practical countability. However, for the purposes of this introduction, we are dealing with sets where counting is feasible. We've kept our examples simple and manageable so you can grasp the core concept. In more advanced mathematics, you'll encounter more complex scenarios, but for now, we're focusing on sets where you can clearly and easily determine the number of elements. So keep these common mistakes in mind as you practice identifying finite sets. Remember, it's all about whether you can, at least in theory, list and count all the elements.